Welcome to The Explainer. Today, we're diving into something that sounds, well, impossible. We're going to explore how a backup plan, something designed specifically for safety, could be the very thing that brings your entire network to its knees.
It just doesn't sound right, does it? You'd think adding more connections for safety would be a no-brainer. But in the world of computer networking, that very safety net can turn into a trap, triggering a catastrophic failure that brings everything to a dead stop. All right, so let's get right into this dangerous paradox. Before we can see how it all goes wrong, we gotta understand why we'd even want these extra connections in the network in the first place. I mean, the idea itself is solid. You run some extra cables between your network switches to create more than one path for data to travel. And that means if one of those cables gets accidentally cut or just fails, traffic just finds another way to go. The network basically heals itself. Less downtime, everyone's happy. But, and there's always a but, right? Here's the catch. If you don't have something smart managing all those extra paths, you create loops. And a loop in a network isn't a fun roller coaster ride, it's more like a feedback machine from hell. Okay, so what really happens when a normal piece of data gets trapped in one of these loops? Well, you get something called a broadcast storm, and trust me, it's every bit as bad as it sounds. And this is where it gets crazy. It all starts with one computer sending out a single broadcast message, something that happens all the time on a network. Now, a switch's job, by default, is to forward that message out of every single one of its ports. When you have a loop, that message hits another switch, which does the exact same thing, and then it comes back around and again and again. That one little packet starts multiplying exponentially until it's an absolute flood of data that just chokes the entire network. Yeah, we're not talking about your internet just being a little slow here. This is a total network meltdown. All the network's capacity, all its bandwidth, is eaten up by these screaming looping packets. No new legitimate traffic can get in or out. The very thing you added for safety has just completely destroyed your network. And if that wasn't bad enough, something else is happening that's just as destructive. Your switches keep this internal address book called a MAC table that tells them where every device is located. But during a storm, the switch sees the same device's traffic coming from multiple directions at once. It's like seeing your friend instantly appear in 3 different doorways at the same time. The switch just panics, constantly rewriting its address book, and has no idea where to send anything. It's pure chaos. Okay, so this begs the question, right? How can we have our cake and eat it too? How do we get the safety of those extra physical links without unleashing this digital hurricane? Well, the answer is a really clever protocol called spanning tree, or STP for short. And honestly, the best way to think about it is like a super intelligent traffic cop for your entire network, one that knows how to prevent gridlock. And this is the magic of STP right here. It doesn't go around and unplug cables. Physically, everything is still connected, all ready to go. But logically, it tells the switches, hey, see that path over there? Just ignore it for now. Pretend it doesn't exist. It puts that path on standby, and just like that, the loop is broken. So how does it actually do that? How does STP build this safe, logical map? Well, it's actually a pretty cool process. The switches all talk to each other and hold, believe it or not, an election. Yeah, it all happens in 3 main steps. First, like I said, there's an election to choose one switch to be the boss, the root switch. Think of it as the center of the universe for the network map. Then every other switch figures out its absolute fastest, most direct path to get to that root switch. And finally, for the crucial part, any other paths, any of those redundant links, they get blocked, put on standby. So, how does a switch win this election? Well, each one has something called a bridge ID. It's made of 2 parts, a priority number and its unique MAC address. The winner is the switch with the lowest bridge ID. So, as you can see here, if all the switches have the same default priority number, it comes down to a tiebreaker. Whichever switch has the numerically lower MAC address wins. It becomes the root. Okay, so once the boss is chosen, every single port on the network gets assigned a specific job. The root port is basically the on-ramp to the superhighway leading straight to the root switch. Designated ports are like the main roads that forward traffic on a local street. And then you have the alternate port. That's our backup route. And its job, for now, is to be blocked. It's the closed road that prevents the traffic loop. And boom, that's it.
The whole network has now converged. You've got all the safety of those physical backup cables, but a smart, logical map that's completely immune to storms. You really do get the best of both worlds. Now, STP was an absolute game changer, but the original version wasn't perfect. It was a little slow. So let's look at how it evolved over the years to get faster and a whole lot smarter. First, let's just appreciate our hero, STP, in action. That broadcast message starts to travel around, but as soon as it hits that blocked alternate port, bam, it just gets dropped. That port is like a bouncer at a club. Nope, you're not on the list. The storm is stopped cold. But what happens when a good link fails and you actually need that backup path? And this was the original STP's big weakness. It was based entirely on timers. So when a main link went down, the network had to wait and wait for timers to expire before it could open up that backup path. We're talking up to 90 seconds of downtime. In today's world, that is an absolute eternity. So naturally, it had to get faster. Enter Rapid Spanning Tree Protocol, or RSTP. It completely throws out those slow, passive timers. Instead, when a link fails, the switches start talking to each other immediately. They use this quick proposal and agreement system to figure out the new map. The result? Convergence time drops to 10 seconds, sometimes even less. A huge, huge improvement. But the evolution didn't stop there. The next big step was MSTP, or multiple spanning tree. It solves a really important efficiency problem. With regular STP, you might have expensive backup links that are just sitting there, blocked, doing nothing unless something breaks. That's kind of a waste, right? Well, MSTP's brilliant solution is to let you run multiple spanning tree games at the same time. You could say, okay, for all my video call traffic, switch A is the boss, but for all my regular data traffic, switch B is the boss. This forces the network to use different paths, making sure you're actually using all those links you paid for. It's true load balancing. So when you step back and look at it, spanning tree is pretty amazing. It took this massive network-killing paradox, this dangerous side effect of redundancy, and completely flipped it on its head, turning it into one of the most important tools we have for building reliable, self-healing networks. And that really leaves us with something to think about, doesn't it? The whole story of spanning tree, from its slow start to its smarter versions, is about making our digital infrastructure more intelligent and more automated. As our world gets ever more complex and connected, you have to wonder, what's the next leap forward in building these truly resilient, self-healing systems?